हॅलो स्टुडंट्स, लास्ट लेक्चरमध्ये आपण सेकंड कोलिगेटिव्ह प्रॉपर्टी स्टडी केली होती, इलिव्हेशन इन बॉइलिंग पॉईंट. In today's lecture, we are going to study the third colligative property, that is depression in freezing point. आता डिप्रेशन इन फ्रीजिंग पॉईंट जर आपल्याला समजून घ्यायचं असेल तर त्याआधी तुम्हाला फ्रीजिंग पॉईंट म्हणजे काय माहीत असायला पाहिजे. यू शुड नो द डेफिनेशन ऑफ फ्रीजिंग पॉईंट. फ्रीजिंग पॉईंट इज द टेम्परेचर ॲट विच liquid is in equilibrium with solid, or vapor pressure of both the phases are same. That temperature is considered as a freezing point. असं टेम्परेचर ज्या टेम्परेचरला लिक्विड सॉलिड सोबत इक्विलिब्रियम मध्ये असतो आणि दोघांचं वेपर प्रेशर इक्वल असतं त्या टेम्परेचरला आपण फ्रीजिंग पॉईंट म्हणतो. ही डेफिनेशन तुमच्या लक्षात असायला पाहिजे. 11th स्टँडर्डमध्ये आपण पाहिलेली आहे, स्कूल लेवलला सुद्धा पाहिलेली असेल. नाव here there is a depression या शब्दाचा अर्थ असतो डिक्रीज. there is a decrease in a vapor pressure. There is decrease in a freezing point. There is decrease in a freezing point. Why there is decrease in a freezing point? What is the reason behind it? Suppose there is one solution. To prepare that solution, we take pure solvent and we added non-volatile solute into it. समजा नॉन व्होलाटाईल सोल्यूटला प्युअर सॉल्व्हंटमध्ये ॲड केलं तर सोल्युशन तयार झालं. पण ज्यावेळी सोल्युशन तयार झालं त्यावेळी प्युअर सॉल्व्हंटपेक्षा सोल्युशनचा जो फ्रीजिंग पॉईंट होता तो डिक्रीज होताना आपल्याला दिसला. आता इथे फ्रीजिंग पॉईंट डिक्रीज का होतो आणि सोल्युशनमध्ये ही प्रॉपर्टी काय अपियर होते, हा सगळ्यात मोठा प्रश्न आहे. ज्यावेळी नॉन व्होलाटाईल सोल्यूट पार्टिकल आपण ॲड करत असतो सॉल्व्हंट, प्युअर सॉल्व्हंटमध्ये, at that time what happened? The particles of the non-volatile solute occupy the spaces present between the solvent particle. Solvent particle मध्ये ज्या स्पेसेस असतात त्या स्पेसेस नॉन व्होलाटाईल सोल्यूटचे पार्टिकल ऑक्युपाय करतात. and due to that the force of attraction between solvent particle get disturbed. the force of attraction जो असतो तो काय होईल, डिस्टर्ब होईल. आता जर फोर्स ऑफ अट्रॅक्शन डिस्टर्ब झाला, they cannot come close to each other easily. They required less temperature. If there is less temperature, then only there is a chance of come close to each other. And due to decrease in a force of attraction between the constituent particle of the solvent particle, they cannot be easily freeze. To freeze or solidify those solvent, that solvent, there is a requirement of a less temperature, and that less temperature is nothing but a freezing point. And that's why we are going to conclude here that there is a decrease in a freezing point. जर पार्टिकल मध्ये अट्रॅक्शन नसेल तर ते जवळ येऊ शकत नाहीत, ते जवळ येऊ शकत नाहीत म्हणजे सॉलिडिफाय होऊ शकत नाहीत, आणि सॉलिडिफाय होऊ शकत नाहीत म्हणजेच फ्रीज होऊ शकत नाहीत, आणि फ्रीज होऊ शकत नाहीत म्हणजेच त्यांचा फ्रीजिंग पॉईंट जो आहे तो काय झाला, आता डिक्रीज झाला. कारण 0 डिग्रीला जर ते फ्रीज होत नसतील तर आपल्याला आणखी टेम्परेचर खाली न्यावं लागेल म्हणजे ते एकमेकाच्या जवळ येऊ शकतील, आणि जर ते एकमेकांच्या जवळ आले तरच तिथे काय होऊ शकते, फ्रीजिंग होऊ शकते. पण त्यासाठी आपल्याला टेम्परेचर डिक्रीज करावं लागेल, आणि यालाच म्हणायचं डिप्रेशन इन अ फ्रीजिंग पॉईंट. इन टर्म्स ऑफ लोअरिंग ऑफ वेपर प्रेशर जर आपण घेतलं, नॉन व्होलाटाईल सोल्यूट प्युअर सॉल्व्हंटमध्ये ॲड केला की वेपर प्रेशर काय होतं, डिक्रीज होतं. वेपर प्रेशर डिक्रीज होतं याचा अर्थ सॉल्व्हंट पार्टिकल सहजपणे वेपराईज होऊ शकत नाहीत, त्यामुळे वेपर प्रेशर क्रिएट होऊ शकत नाही, म्हणून वेपर प्रेशर डिक्रीज झालं असं आपण म्हणतो. आणि जर पार्टिकल वेपराईज होत नसतील तर स्वाभाविक आहे ते ॲज इट इज सोल्युशनमध्ये राहत असतील, दे कॅनॉट क्रिएट वेपर प्रेशर. अँड ड्यू टू लेस वेपर प्रेशर they try to freeze, but for freezing there is a requirement of less temperature, and that's why there is decrease in a freezing point. There is a decrease in a freezing point. तर हे झालं प्रॅक्टिकल व्ह्यू झाला किंवा थेरॉटिकल व्ह्यू झाला डिप्रेशन इन फ्रीजिंग पॉईंटचा. सपोज आय एम गोइंग टू एक्सप्लेन दिस टर्म मॅथमॅटिकली. आता मॅथमॅटिकली टर्म एक्सप्लेन करायची असेल तर परत एकदा आपल्याला सोल्युशन कन्सिडर करावं लागेल. सपोज आय हॅव वन सोल्युशन वेअर नॉन व्होलाटाईल सोल्यूट इज ॲडेड टू द प्युअर सॉल्व्हंट अँड फॉर दॅट सोल्युशन सपोज T0F will be the freezing point of the pure solvent. T0F ला मी freezing point of the pure solvent म्हणतोय. TF ला freezing point of the solution म्हणतोय. TF is the freezing point of the solution. आता जर आपण या दोन्हीचं कंपॅरिझन केलं तर प्युअर सॉल्व्हंटचा जो फ्रीजिंग पॉइंट असेल तो सोल्युशनच्या फ्रीजिंग पॉइंट पेक्षा कसा असायला पाहिजे, ग्रेटर असायला पाहिजे. कारण सोल्युशन तयार झाल्यानंतर तर फ्रीजिंग पॉइंट मध्ये डिप्रेशन डिक्रीज पाहायला मिळते. म्हणजेच TF इज लेस दॅन T0F और T0F इज ग्रेटर दॅन TF. आता या दोन्हीतला जर डिफरन्स घेतला आपण दॅट इज डेल्टा TF. The difference between the freezing point of the pure solvent and freezing point of the solution is nothing but delta TF, which is called as decrease in a freezing point, and that's why delta TF indicates decrease in a depression in a freezing point. And from this mathematical expression we can mathematically define depression in freezing point as it is the difference between freezing point of the pure solvent and freezing point of the solution. This is the mathematical aspect for the depression in freezing point. Now we are going to study another mathematical aspect, another mathematical relationship between the depression in freezing point and molar mass of the non-volatile solute. Molar mass of the non-volatile solute is m2, depression in freezing point is delta TF. Here also I have that solution which consists of pure solvent in which non-volatile solute is added. Delta TF will be the depression in freezing point, m2 will be the molar mass of the solute, and m1 will be the molar mass of the solvent. m1 will be the molar mass of the solvent. These are the considerations. W1 and W2 are the given masses of the solute and solvent respectively. W1 and W2 given masses or the masses used in the solution of the solute and solvent and solute, sorry, here solvent and solute respectively, solvent and solute respectively. Okay, one stand for the solvent, two stands for the solute. As we know, any colligative property depends on number of solute particles, and if it depends on number of solute particle, it means it depends on number of moles of solute particle also, because number of moles of solute particle depends on number of particles. And if it depends on number of solute particle, that means it depends on molality also, because here all the terms are given in the form of mass and all the terms are given in the form of number of mole or mass. That means it depends on molality, and so that we can say that delta TF is directly proportional to the molality, that is small m. Then we can write it as delta TF is equal to KF. Here introduction of proportionality constant, that is KF into m, and that is equation number 1. Delta TF is equal to KF into m, where KF is called as proportionality constant, or it is also known as molar depression constant, or it is also known as cryoscopic constant. Okay, but m, molality is nothing but the number of moles of solute. Number of moles of solute are indicated by n2, number of moles of solute present in 1 kilogram of solvent, present in mass of solvent in kilogram. Mass of solvent is W1, and that's why the formula is m is equal to n2 upon W1 in kilogram. Suppose the given mass of the solvent is in gram, then we can write it as n2 upon W1 into 10 raised to minus 3. For that kilogram, gram to kilogram means into 10 raised to minus 3. But n2 is equal to W2 upon m2. Number of moles of solute is equal to given mass of solute upon molar mass of solute, W2 upon m2, and that's why molality becomes W2 upon m2 into W1 into 10 raised to minus 3. And if the molality is equal to W2 upon m2 into W1 into 10 raised to minus 3, that means equation 1 becomes delta TF is equal to KF into W2 upon W1 into m2 into 10 raised to minus 3, and that is the relationship between delta TF and m2. Suppose all these values are given, we can say this is the relationship between delta TF and m2. Suppose all these values are given, m2 can be calculated. And the technique in which molar mass of the non-volatile solute is calculated using depression in freezing point, that technique is called as cryoscopy. That technique is called as cryoscopy technique. Here we can put this 10 raised to minus 3 into the numerator, and formula becomes delta TF is equal to KF into W2 into 10 raised to 3 upon W1 into M2, and that is also the relationship between delta TF, depression in freezing point, and the molar mass of the non-volatile solute. We can see this equation once again. Suppose I have a binary solution containing non-volatile solute present in a pure solvent. M2, M1 are the molar masses of the solute and solvent respectively. W2 and W1 given masses of the solute and solvent respectively. As per the definition, delta TF will be directly proportional to the molality, and if delta TF is directly proportional to the molality, delta TF is equal to KF into M, where KF will be the proportionality constant known as molar depression constant or cryoscopic constant. But molality, according to the definition of molality, molality is equal to N2 upon W1 in kg. But suppose the given mass of the solvent is in gram, then the formula becomes N2 upon W1 into 10 raised to minus 3, and so but N2 is equal to W2 upon M2, and so that M becomes W2 upon M2 into W1 into 10 raised to minus 3, and that's why equation 1 becomes delta TF is equal to KF into W2 upon W1 into M2 into 10 raised to minus 3. If 10 raised to minus 3 get into the numerator, then it will become delta TF is equal to KF into W2 upon W1 into 10 raised to 3 upon M2, and that is the relationship between depression in freezing point and molar mass of the given solute. Now here from the equation 1, we can write it as a KF is equal to delta TF upon M. Delta TF upon M. Suppose M is equal to 1. Suppose M is equal to 1, and that's why KF is equal to delta. KF is equal to delta TF. And if KF is equal to delta TF when M is equal to 1, from this expression we can define molar depression constant or cryoscopic constant as it is the depression in a freezing point. It is the depression in a freezing point for 1 molar solution. It is the depression in a freezing point for 1 molar solution. That will be the definition for cryoscopic constant. And the unit for the cryoscopic constant will be, from this formula we can calculate the unit for the cryoscopic constant. Delta TF, it is the temperature, and temperature normally taken in a Kelvin or degree Celsius. Molality, for molality there is formula. What is that for? What is the unit for molality? For molality, unit will be mole upon mass in kilogram. That's why mole per kg. And due to that, the unit for KF will be Kelvin kg per mole. Kelvin kg per mole. Like that, ebullioscopic constant or molar elevation constant, here also unit of KF is Kelvin kg per mole. This unit should be in your mind, because for NEET and CET it is very important. You should know the unit of elevation constant, molar depression constant. You should know the definition of molar elevation constant and depression constant. It is the depression in freezing point for 1 molar solution. This is all about the depression in freezing point. I think this concept is clear. If you have any query or doubt, you can contact me on my personal number. This is all about the depression in freezing point, and for today I think it is sufficient. For tomorrow's lecture, in tomorrow's lecture we will conduct the next colligative property, that is osmotic pressure. Okay, so have a great day. Thank you so much.